This is part 2 of the video notes for Objective 2B, Graphing Exponential and Logarithmic Functions. In this section of the notes, we're going to focus specifically on graphing a logarithm as the inverse of an exponential. We want to be able to graph logarithms both by hand and with our graphing calculator. So the first example we're going to start off with is f of x equals 2 to the x power. Build a table and you get 0, 1 as the initial value, 1, 2, and 2, 4. So the exponential function is here. And the way we graph a logarithmic by hand is by finding the inverse of its exponential function. I've given you a second graph, but I'm actually going to produce my logarithm on the same picture just by using a different color. So if you don't have two colors, you can draw your logarithm on the other graph that has been provided. If a logarithm is the inverse of an exponential, what exactly does that look like? Well, we're going to take a break from this and just talk about the inverse relationship between a logarithm and a function, which we reviewed over in the 2a notes as well. An exponential function is any function in the form of y equals a to the b power. A logarithm, using the same letters and variables, would be log of the same base of the exponent, or of the argument, equals the exponent. So a logarithm is a way for us to isolate the exponent of an exponential function. If a log is the inverse of an exponent, to graph this one, we would just need to inverse this table. That means we would graph the ordered pair 1, 0, 2, 1, and 4, 2. Then we want to be sure that we're identifying our asymptote. The x-axis is the asymptote of 2 to the x, so the y-axis is the asymptote of our log. And this is our first hand-graphed logarithm. Go ahead and take out your graphing calculator and go to your y equals function. Your ln button, or your natural log, is next to the 4, and you just type ln of x. When you graph, we should be set the standard setting, and you should see what actually looks like a square root function. It's up to you to make sure your logarithm looks like a logarithm and has an asymptote where it's supposed to. So I'm going to take a peek at this table, and I find that this one also has the point 1, 0, but instead of being at 2, 1, it's 2, 0.69, and instead of 4, 2, it's 4, 1.3. And I'm going to just graph 0, 1, and 2, not 0, 1, 2, and 3 as my 3 points. So 3 is at 1.1. My asymptote is where the error occurs, so you can see the first error is at 0, and I'm not going to cross the y-axis. Now, depending on your calculator, you can also graph logarithms other than ln that have a different base by typing math and searching for the log base function. Now, my calculator is older, and I don't have the log base function. But if you have a newer calculator, it should be down in this menu somewhere over here after you press the math button. For the next examples, we just want to practice graphing logarithms by hand. And so we have 4 examples to work through in example 8. So 4 different functions. And we're going to start with f of x equals log base 5 of x plus 2. Now each of these functions represent a different transformation. The first one, we've got our plus 2, which is a left 2. Our second one, we have a plus 2 on the outside. Our third one is a reflection, and our fourth one has 2 transformations. So how can we create an inverse of this equation? Let's start by writing f inverse of x. The base of this is let's start by switching x and y. X equals log base 5 of y plus 2. Then rewrite the equation as an exponent. 5 to the x power equals y plus 2. When you're taking an inverse, your input becomes your output, and your output becomes your input. Last step is to subtract 2, and I'm going to go ahead and flip the function. F inverse of x equals 5 to the x minus 2. So now we're looking at an exponential function with an initial value of 1 that's been shifted down 2, and a pattern of times 5. This is something that I can table by hand and graph by hand. Zero, 1, and 2 are good points. 0, you should get 1 times 5 is 5, times 5 again is 25. Then I want to shift this down 2, and I'm just going to do this right here in my table instead of doing it on the graph. 1 minus 2 is negative 1, 5 minus 2 is 3, and 25 minus 2 is 23. When you go to sketch the graph, remember that this table represents the inverse of the logarithm you want to graph. So when you graph it, make sure that you inverse the points again so that you're actually graphing the logarithm. Does this function, let's start with the first point, negative 1 comma 0. The second point, 3 comma 1. And then with logarithms, you generally can't fit 3 points on the graph without an unusual scale. So logarithms are where I make the exception to the 3-point rule. Make sure you have at least 1 point and your asymptote. Where's the asymptote to this function? This is left 2. And if you take your y-axis and you shift it to the left 2, you find that the asymptote is over here at x equals negative 2. And there's the graph of our logarithm. Let's take a look at example B, or part B of example 8. So this example says f of x equals log base 2 of x plus 2. And you have a graph. And we want to find the inverse. So the first step is always to invert this function. The more often you take the inverse, the easier it gets. We're going to do x equals log 2 of y plus 2. And then before we can rewrite it as an exponential, we can't actually do that until the log has been isolated. So we're going to subtract this 2 over to the other side. Because if you're thinking in terms of solving this equation, minus 2 would be the step that you did before you did things like square rooting or dividing. This would always be the first step. So we've got x minus 2, and I'm going to purposefully put that in parentheses to group it together, so that when I rewrite this, I realize this is the entire exponent. We've got 2 to the x minus 2 power equals y. Let's graph this function. I know that these are the exponents of 2, so I'm going to do 0, 1, and 2. And again, I'm going to ignore the right 2 shift until I'm ready to graph. I've got x, y. 2 to the 0 is 1. 2 to the first power is 2. And 2 squared is 4. And then I want to take these ordered pairs and I want to move them to the right 2. And moving to the right 2 would mean adding 2 to all of my x's. When I go to graph this, I have to remind myself that these are the inverse values. Now the worst case scenario is that you graph these points on your grid, and the best case scenario is once you've done that, you realize you've graphed an exponential and you inverse your exponential to get your final answer. But I like to inverse right from the table. So I'm going to take these ordered pairs after my right 2 shift, and I'm going to switch them. My first point will be 1, 2. My second point will be 2, 3. And my last point will be 4, 4. Where's my asymptote? Now a log normally has an asymptote at the y-axis. When you shift it left and right, it's no longer at the y-axis. But this shifts the log up. So I should still have an asymptote in the same position, because moving a y-axis up and down doesn't change its position. Part C of the examples is our reflection. So we want to graph y equals negative log x. Now this is the first log example we've done that doesn't have a number and the base, and that's because this log is naturally base 10. Any log without a base number is base 10, which is our base value when we count. So when I go to switch x and y, I have to try and get the y by itself as much as possible, so I'm going to distribute a negative to both sides of the equal sign, and then I'm going to inverse, which becomes 10 to the negative x power equals y. So I'm going to graph this function, and there's a few ways I can approach this. I know what a negative exponent does to an exponential graph because it turns it into decay. But I also know what a negative does to any parent function. It reflects it over the y-axis. You have to decide what the best way for you to handle this is. One thing I know for sure is when I'm dealing with a negative exponent, I want to pick negative values on my scale. So I'm going to plug in -2, and I'm going to let the negative be a part of it. 10 to the negative 2 power is 10 squared. That's definitely not going to fit on my graph. 10 to the negative 1 is 10 to the first power, which is 10. 10 to the 0 is 1. And 10 to the negative first is 1/10, or 0.1. So these are the 3 points I'm going to use to graph this logarithm. Start with the point 10, -1. Not really going to fit on my graph. 1, 0 does, and 1, 0.1, 0.1, 1 does. What does this graph look like? I don't really have a lot of points. Now, even though I can't fit 10, -1, I know that it's down here off to the right somewhere. So that tells me this function is going down here to the right somewhere, and by -1, it's way off the graph. I also know where the asymptote of this function is. A logarithm has a natural asymptote at the y-axis, so this part of the function must extend upward like so. What does this negative do to your log? It flips it over the x-axis. A log would have typically looked like that, and now ours looks like that. So this is our first graph of logarithmic decay. This is an example of what a log decay function looks like, since it decreases across its entire domain. The last example is to graph f of x equals log base 2 of x minus 1 minus 3. So I've got a right 1 and a down 3 shift. And if I wanted to, I could graph the logarithm without this shift. So in the last couple of examples, when we took the inverse, we included these values. And this time, I want to try excluding them and see if that gives us something simpler to deal with. So we're going to just graph this portion. The inverse of a log base 2 is 2 to the x. The table for 2 to the x is 0, 1, 2, 1, 2, 4. So the logarithmic table, or the logarithmic points, are 1, 0, 2, 1, and 4, 2. Graph each of these points, but shift them to the right 1 and down 3. So my first point is at 1, 0, and then 2, 1, and then 4, 2. And I'm just going to sketch the parent logarithm.
And then I'm going to shift the parent logarithm to the right 1 and down 3. Right 1, down 3, right 1, oops, that's not down 3. Right 1, down 1, 2, 3. Right 1, down 1, 2, 3. Right 1, down 1, 2, 3. Before I connect these, I need to know if my asymptote has changed. So if you move your asymptote right 1 and down 3, is it in a new position? And the answer is yes. Redraw that asymptote and make sure that you don't cross it as you continue your graph. This concludes the video notes for part 2 of Objective 2B, which was graphing exponential and logarithmic functions.